So in the last class, I have introduced you about the overall structure of the labs, what all are what all experiments we are going to do, and I know that yes, tell me. And I know that you guys are from several other backgrounds, such as computer science, maybe civil. You may face difficulty while understanding mechanical concepts in a while, but in the meantime, I will try to be at more scratch level or maybe more basic level so that you guys can connect with me. And if you face any difficulty, I'll still go slow. Okay, in the first lab, usually we take this lab in offline mode, but since this is online, we try to take up things uh, in certain way. Okay, we'll see how it works in online way. So let me first uh, so I have already shared this EME lab manual with you guys. Everybody has this. So all the experiments you will be doing are listed in the manual form in this particular PDF, which I have already shared in the Teams as well. Let me show you where you can find this file. You have to go to Teams, and in Files, after this, right to the post, you have a File section, and here you have all the class materials. This is your EME lab manual for all the experiments. Okay, I will switch off my video so that I can write things on PDF and on my PPT as well. So we are going to talk about in today's experiment, that is experiment number 1. The title of this experiment is to analyze the uh, fluid properties, probably in more precise sense, uh, thermodynamic properties. So the objective of this experiment is to understand and perform fluid property evaluation using property table, okay, engineering equation solver software that I have already sent you a link on WhatsApp group, and also using MATLAB if at all we have, or there are other alternatives. We have Scilab, other mathematical computational tools we have, such as in analogy with MATLAB are Scilabs and Octave Online. Okay, this MATLAB and this EES is actually a proprietary software. But the Scilab and the Octave Online is open to all. It's freely available. Okay, but first we will not talk in. In the first half we will try to understand the concepts uh, behind understanding the fluid properties evaluation using property tables. Property tables, you may get these property tables in any textbook such as Sengel, Introduction to Thermodynamics. Okay, so this is the book. I have an ebook also. I can share it with you guys in WhatsApp. Uh, in the appendix section, we have this property table with us. Let me show you that also. So this is your, I've already, this is the property table we are going to use. Okay, we'll see how we are going to work with these property tables after some time. So in order to understand the fluid properties, we first have to understand the concept of pure substance first. So I have a, PPT. So this is cumbersome to read or to follow. I have a PPT to make sure that you guys should be able to understand quickly. So first of all, you should ask this question: why should I know the properties of the properties, rather to be more precise, thermodynamic properties of any given substance? Okay, and or a priori, what are these properties actually? What all properties we are interested in? So the properties we are interested in thermodynamics are usually temperature, pressure, specific volume or total volume, entropy, enthalpy, etc. So these are the major properties we are interested to know. And why should I know these properties? That should be our first question. Why should I know this? I mean, let's suppose I have a beaker full of water. Then why should I know at what temperature it has? I mean, what is the temperature it contains? Or let's suppose it is having some piston on top of it. And so I am also interested to know the pressure at what pressure this water or air that is trapped inside this piston cylinder arrangement. Okay, I need to know the specific volume. So volume or specific volume. So specific volumes uh, are the I mean, it is defined as the total volume divided by the mass of the substance. So this is volume per unit mass is called specific volume. So this is you can say a culture to denote things into specific volume rather than total volume in thermodynamics course as such. Okay. Before this, shall I ask you guys what is thermodynamics all about? Because you guys might be new because you guys are from computer science or some other backgrounds, so you might not be knowing. So can somebody tell me, I mean, if you at all you have studied something, some thermodynamics in your 11th, 12th or in your 9th, 10th. So what do you mean by thermodynamics? Why do we study this subject? Can someone state?
It is the study of energy.
Wow, very, thank you. So you are correct. So this is a branch of science that deals with study of energy. Okay. So energy uh, are often associated with temperature, pressure, specific volume, entropy, enthalpies are often associated. Not exactly, but maybe implicit way or explicit way. That is why, and again, we should also ask. I mean, okay, fine. I have studied thermodynamics subject. So what? What I'm gaining out of it? Okay, so the answer to this question is by studying the thermodynamics, you will be able to design several thermodynamic components, such as you are right now you guys are peacefully sitting in your room, and you have switched on your ACs in your room, and you are comfortably sitting in it. So AC, your air conditioning unit, is essentially a thermodynamic uh, system. Okay, it deals with energy. It takes away some energy. It 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 cools down your throws cold air. Okay, based on some mechanism we'll not discuss right now, but yes, in order to understand, or in order to design and analyze your air conditioning system, you should know, uh, you should have a knowledge of thermodynamics. Okay, and in order to have the knowledge of thermodynamics, you should know these properties, basically temperature, pressure, volume, uh, entropy associated with, enthalpy associated with those terms. I'm not going to tell you what these terms are, because these are more basic and you can actually look into. So enthalpy is something overall heat content, entropy is something related to the uh, randomness of the molecule at molecular level, volume, that what it occupies, pressure, uh, how much the momentum exchange the your molecules are doing at the walls of your substance, which is at where it is kept. Okay, it's kind of overall average momentum transfer that is occurring uh, on the walls of the substance that is kept it by the molecules of it. Temperature is again the overall kinetic energy that the molecules possesses in average sense, that comes out to be temperature in a macroscopic way, although it derives, it is derived from microscopically from the kinetic energy that your molecule possesses, from where it has been derived, and we can see it macroscopically as a temperature. So these are all things you can actually read through in your textbooks. Fine. So far, so fine. So yes, so we're looking at why we actually want to study this subject. So because to design several thermodynamic systems, such as your AC is the very cool example. Maybe again your fan, uh, maybe like your electricity is coming at your home through some sort of power plants. Okay. So all these things, power plants, refrigeration systems. Okay, all these requires uh, knowledge of what? Fluid properties. Okay, these properties you need to know a priori, so that you can very well or efficiently design your equipments. Not only that, you can also judge your efficiencies if you have proper knowledge of these properties. Although this thermodynamics is a very vast subject, I cannot tell you in one class, because it's a whole course. So I want to skip some things, but I'll try to make things more comfortable, since you guys are not from mechanical background. I agree that, but let me know if you face any difficulty in between. So the first thing I'm going to talk about in this thermodynamics is the pure substance. Okay, so just ignore this chapter 3, because I have taken this PPT from my previous thermodynamics lecture. That's fine. I can strike that off. Uh, Pure substance. So we are more interested in. So you may have a mixture of substances, but we are more interested in pure substances. Okay, because the working fluid in refrigeration or in power plant are often uh, comprised of pure substances. So this is not pure substance of in literal sense, but pure substance in thermodynamic sense. Okay. So in thermodynamics, pure substances are substances whose chemical compositions are homogeneous. That's all. The substance whose chemical composition are homogeneous throughout, I'll tell that this substance is pure. Whenever I'll see the chemical compositions are in some sort of inhomogeneity is there, I'll tell that this is not a pure substance. So let's suppose in a beaker you have nitrogen gas, it is kept tightly. This is a pure substance, yes. So every portion, you take every portion anywhere, you'll get the same N2 everywhere. Then I'll ask, what about air? Can somebody tell if air is a pure substance? I'll tell yes. Why? If you do chemical analysis, if you take this region and if you do the chemical analysis, you will see that you will have, let's suppose 71% nitrogen, 21% maybe oxygen, maybe 1% organ, 0.1% carbon dioxide, and etc. So it has a fixed chemical composition. I know that. I'll take the same amount of air from this region. Let's suppose this is region 1, this is region 2. I'll see that the same composition I find it here also. Okay, in the air also. So I'll tell that yes, this so far so good. N2 and air both are uh, pure substance, and I can tell you that air can also is used more often as a working fluid in several components. Next thing is water. So water, in general, water uh, in power plants, if you see in boil, so power plants have several components. Such components are boilers, condensers, etc. Okay. So in boiler, the water coexist as a liquid and vapor form at the same time. Okay, it to and fro, it it evaporates as a water and it may come back as a liquid form. So it again it has what same chemical composition. If you take out the things from here, you'll see you'll have H2O only, and here also you'll see things have H2O only, whether it is gas or vapor form or the liquid form. Okay, so again this is also a pure substance. And lastly, if the air is uh, you have a liquid air, some sort of liquid air, and obviously normal air, this is vapor of normal air. I mean the air which is having in gaseous state, air which is liquefied, if it is mixed in a container, this we cannot tell this as a pure substance, since if I take this thing air, so this has same chemical composition which I have written over here, but when I take up do the things chemically, if you want to observe the things chemically, we see that it has lesser argon or CO2 components. Okay, slightly different. We don't know, and it has, you have to further look into the literatures, but yes, it does not have same chemical composition, does not have. So it's not a pure substance. So we'll not take this as our working fluid as if the air is in liquid form. But that is the another case. So we'll now quickly switch into, because our aim is to look into the fluid properties evaluation. I want to know the fluid properties through tables. That is why we will move quickly to this particular uh, uh, slide. So when I talk about water, so water, what I will do is I will do an experiment. In order to understand the fluid properties, let me do an experiment, a quick experiment. In this experiment, what I will do is I will keep the water at pressure 1 atmosphere and temperature, initial temperature was 20 degrees C. So the temperature and the specific volume I am going to plot on this particular plot. Okay, in this scales, this temperature and this is specific volume. It has certain specific volume. Let's suppose it has certain specific volume V1, and this is the state you are talking about 1. This is at state 1, at state 1. Okay, and the pressure I kept it 180 m fixed by fixing the mass of the piston on top of it. Now what I will do is I'm going to add heat into this particular piston cylinder arrangement. This is some sort of piston cylinder arrangement is kept, and usually you can get a feel of why this is more uh, taken into account, because your internal combustion engines, IC engines, uh, more precisely works into this some sort of piston cylinder arrangement itself. So you can take a analogous feel of why we are doing this experiment. Okay. Now what happens here is, in general, uh, in order to fix the state. So what do you mean by fixing a state? Let's suppose, uh, anybody tell me your name and roll number, or maybe any name quickly. We don't have much time. Any name? Volunteer who is here?
Vaidehi Desai.
Okay, Vedahi. Okay, so Vedahi, who reads in PDEU or PDPU, will be different from other Vedahi who is studying at IIT Gandhinagar. Right? Am I right? So I want to distinguish between this Vaidehi and this Vaidehi. How should I do that? So I'm going to fix it by telling that this Vaidehi has some certain characteristics. Okay, this Vaidehi is, let's suppose, 20 years old, and she is female, and she is 5 feet 6 inches tall. Now I'm going to fix that. Okay, yes, now this Vaidehi might be fixed, but this Vaidehi might have certain other characteristics. Right? So in similar way, we are going to fix the state. We should fix the state of any substance by using the properties or the characteristics. And what are those characteristics? Maybe temperature, pressure, specific volume, uh, entropies and enthalpies. So the most obvious ways are temperature, pressure and specific volumes. So if at all you know temperature and volume of a simple substance, okay, you are done. You are going to fix a state. So I am fixing this state 1. Let's suppose you are to plot 1 comma 1 on a coordinate axis. So once you have 1 comma 1, I know that I have to traverse 1 here and traverse 1 on top, and now I have fixed my state. 1 comma 1 is fixed. Similarly, if you want to fix thermodynamically, you want to fix, I mean, you want to characterize that, okay, this system is at certain state. You should know two properties. Okay, I know the temperature, I know the specific. Now this is fixed. Okay. Now what I will do, I will start adding the heat. What it should do? Can somebody tell? It's obvious. Its temperature is going to be rise, right? Also its volume is going to be rise. ओके, स्लाइट ये पिस्टन ऊपर उठेगा क्योंकि एक्सपैंड होगा ये गैस, और रादर ये वाटर एक्सपैंड होगा, टेम्परेचर भी बढ़ेगा, स्पेसिफिक वॉल्यूम भी बढ़ेगा. सो आई कैन सी दिस ट्रेंड, राइट? And this will keep on going till it reach 100 degree C, and this 100 degree C is a very peculiar thing, and we will reach certain state called saturated state. Okay, so before saturated state it was in some state called compressed liquid state, and this compressed liquid state is defined as not about to vaporize. Okay, once it reaches 100 degree C, when the temperature reaches 100 degree C, your water is tell that, now water will tell us that, okay guy, I am now in saturated state. What does it mean? I'm no more increasing your temperature. Why? I'm going to change my state now. Change my state from liquid to vapor. Okay, now After 100 degrees, see, whatever temperature or whatever heat you will add from the candle, your temperature, you will notice that even though the specific volume start to increase, the piston start to expand, so V starts to expand, but your temperature fixed is fixed, so it's constant. Why it is happening? Because it undergoes phase change. Okay, and in this phase change, not only we need temperature or volume, but we need one more, another variable to fix the state properly. Why? Because temperature and pressure are no more independent properties, they are dependent. Okay, I'll tell you in later slides uh, why, but you need another variable to fix it. Okay, and this variable or often we call it as x, and we call this x as quality of steam. Okay, so quality of steam is defined as mass of steam divided by total mass. So it seems there was an internet issue. So where I have lost, can somebody tell me? Uh, where I have lost you guys, can somebody tell me? Quality?
Yes, sir. Quality of steam.
Okay, fine. So if at all you are in compressed liquid phase, you no need to worry about uh, third property to fix the state. Only T and V was fine here to fix the state. But here, one more variable you need to know, that is called quality of the steam, which is defined as x. So the quality here at x is equal to 0, mass of steam is 0 over here, and mass of steam is 1 over here. I mean, not 1, sorry, quality is 1 over here at this particular state, and this particular is 1, and it lies between 0 to 1 at all the times. So I'm not going to go into the details. Just I want to give you an overview. I mean, just want to give you a, flavor of the thermodynamic uh, property play arounds, because all the things I cannot explain in one lecture, so that is not possible. But let me give you a flavor of why I'm doing this and what are the criticalities here. Okay, so we need to fix one more. I mean, in order to fix it, we need one more quality for this particular state called saturated mixture. So this mixture phase is called from 2 to 4. I mean, between 2 to 4 is called saturated liquid phase and is called about to vaporize. It is defined as about to vaporize. When we go further, the time comes when all your liquid are going to be converted to vapor. Okay, but your temperature is still at 100, and this state called state 4. Oh, sorry, this is mixture. I already told mixture thing. Okay. Okay, so all the things have been in your liquid has been converted to vapor, and this is this phase at 4, and this phase is called about to condense. Why? Whenever it loses some heat, it is going to get back to this. That is why it is called about to condense. Okay, but notice that still it has temperature 100 over here. Okay, the temperature was still constant at 100. Notice that in all the experiments I have kept my pressure as 1 atm. I did this experiment in such a way that I kept this experiment at all the times at pressure is equal to 1 atmosphere. If we do the experiment at another pressure, the scenario would be slightly different. Anyways, next thing is when we add the heat more, okay, what will happen? Now all the vapors, it is in vapor phase totally, but now it is going to gain the temperature. Okay, now it is going to gain the temperature. How very well, I mean very well analogous where it is in compressed liquid phase, and this phase is called superheated vapor, and this is called not about to condense. This phase is not about to condense. In anywhere it lies anywhere here or here, it is called superheated vapor. Fine. Now this is the last statement I want to put, and then I will switch into the EES software in order to get these values. So in EES software, whenever I type some temperature 100, some pressure 90 kilopascal, I'll get all the fluid properties H, S, V, or any other properties. Okay, we'll see how. Okay, but before that, let me ask you guys one last question in order to summarize this whole concept. I'm giving you a statement that water boils at 100 degrees C, whether this statement is correct or not. So this is please mute yourself. Unmuted. I'm not able to mute it. Please mute yourself. Akhil Jetwa, Akash Patel, please mute yourself. Atharth Modi, Abhijit Meena. Everybody is fine. I don't know. Fine. Something is happening. Okay, fine. Let me proceed because I have to finish this. So when I'm telling that water boils at 100 degrees, this is an incorrect statement because you need to tell, because you need to fix the state, right? You know, you should have two quantities. You should tell that at pressure 1 atm, then only I will tell that at 1 pressure, 1 atm pressure, water boils at 100 degrees C. Whenever you do pressure is equal to 2 atmosphere, you may not get the same scenario. You may get something like this. Okay, at P is equal to 2 atm, P is equal to 5 atm, you may get something like this scenario. Okay, eventually you will see that when you connect these things, you will get a dome like structure. This is called vapor dome. Okay, and this particular line is called saturated liquid line, and this particular line is called saturated vapor line, and which is essential to know to design your certain equipments, or if you are want to analyze your thermodynamic system more closely, you need to have the knowledge of these certain characteristics priori. Okay. Again, at P is equal to 2 atm, your water may boil at some other temperature, 100 maybe 20 degrees C. So that is why if you or at lower temperature, lower pressures, your water may boil at lower temperatures. Okay, maybe 90 or 80 degrees C. So that is why whenever you want to cook your food at top, mountain top, okay, you were trekking, or you went to Mount Abu or somewhere Udaipur, or you hill at some you climbed at some hill, you want to boil some water, you'll see that pressure there is below 1 atmosphere, that is maybe zero point 0.8 or 0.8 atmosphere. So you'll see that at 0.8 atmosphere your boiling temperature is 80 degrees C. So your rice is not going to be cooked at 80 degrees C at any time soon. That is why you need pressure cookers in order to pressurize it additionally and to cook your rice. Fine, now let me not go. Okay, one more thing I want to talk about. This temperature and pressure is corresponding temperature and pressure is called saturation pressure and saturation sorry, saturation pressure, and this is called Tsat, because this is the saturation condition, all these points, and at that pressure whatever it is happening, it is called corresponding saturation pressure. Okay, whenever the phase change happens, it is called. So for 100 degrees C you have saturation pressure 1 atmosphere, saturation temperature 100 degrees C. For 120 you will have another pressure, another temperature. For 5 atmosphere you have another temperature and another pressure. Now let me go quickly to the software part. Let's finish this lab, or maybe I'll do one. I'll quickly do one. So this is how it is. You can go through this lab manual, and we'll do one exercise here. A rigid tank contains 50 kg of saturated liquid water at 90 degrees C. Determine the pressure in the tank and the volume in the tank. How would we proceed? Okay, so this is the only question I will take up. I will not take further questions. I will take this question, and you guys can do it. The next questions, there are 4 questions in it. You can do it later. Okay. So in this question, so we have, let's suppose I have temperature and specific volume. You have a dome. Okay. Now it is given that you have 50 kgs of saturated liquid. So saturated liquid is where? In this particular line, right? Somewhere here, maybe here, I don't know. But the thing is, it should have the information of something like pressure at this pressure, whatever the pressure would be at the rate of this particular temperature, Tsat. Okay. Now it is asking, since this is saturated liquid at temperature 90 degrees C, so this is 90 degrees C. Determine the pressure. You need to find this particular which pressure it is happening and what is the volume of the tank. So volume of the tank I can get it from this information V, right? So these two information I need to look into first into through the property table. Let me quickly go to the property table, and you have in the property table, I'll share that this also. Go to table number 4, A4. Table number A4, saturated water temperature table is given. You have to look into this. You have to be careful. Saturated water, superheated waters are different. Tell me, क्या हुआ? Hello. Okay. Go to 90 degree temperature. Go to 90 degree. What is the saturation pressure you have? This is your answer. That's it. Okay. So your answer is from table. So I will take 10 more minutes and then I will leave from table A4 at temperature 90 degrees C. Since I know that this is a saturation condition, so Psat is equal to 70 point, what was that? 70.183. That's it. Okay. Now I have these two properties in our hand. Now I want to calculate the specific volume or the volume of the tank. So once I have the volume of the tank, I have the mass, I'll divide it, I'll get the specific volume. Or if I want to write the total volume of the tank, I can just multiply with mass, which is given 50 kg times the specific volume. Okay. Now have these two properties with us, we can actually estimate our specific volume by looking at the table again. Let's see how. Okay. Now saturated liquid, this is saturated vapor volume, this is saturated liquid volume. Since I know that this is saturated liquid condition, there are no mixtures, this is saturated condition, so this is your answer. 0.00136. So this is 0.00136. This is kilogram per meter cube. Sorry, meter cube per kilogram times 50 kg, and multiplied you will get, if you do the algebra, you will get the proper answer. But now we are going to validate this result through the EES software or any software. So let me, I hope that you guys already have installed it at your laptop. I have already installed it. Okay, so this is the interface you would look like. Okay. So this is a EES software. Let me quickly tell you how to use this EES software. These are the menus buttons. You are going to take a new file. Okay. So in this, let me write this. Let me write. I'll just take 10 minutes, 5 to 7 minutes. Then I'll leave you guys. I want to solve x plus y is equal to 1. So this is one equation. Next equation is x minus uh, y is equal to 0.5. Let's see. I want to solve this. You just have to write x plus y is equal to 1 and x minus y is equal to 0.5, and let me solve this. So there is a solve button here and continue. It will throw you the answer. That's it. X is equal to 0.75, y is equal to 0.25, and that is correct also. 0.75 plus 0.25 is equal to 1, and 0.75 minus 0.25 is 0.5. Okay, so this is how you are going to do all sorts of algebra. It has all lots of capabilities. Although this is basic, I would request you to learn MATLAB, Octave and Scilab also, but this is just basic thing. So now let's come to the point. In 5 minutes, I'll tell you how to calculate the thermodynamic properties with the EES software. So you have to go to examples. Let me close these things. solutions. Go to examples. Property thermodynamics. Go to properties thermodynamics. You have to select property calculator. There are other calculators as well. Set OK. Somebody is calling. Okay, now this is a already written code is there, in-house code is there. We don't want to do anything. We don't want to hamper it. Okay, now we have what we have. We have temperature. We have, so these are the properties you can actually tell here. So we have temperature here is, let's suppose temperature, how much temperature we had, 90, right, 90. How much pressure we have, how much pressure we have, pressure we have 70 point, let me see it again, how much pressure we have, 70.183. We have the pressure 70.183, and you just have to hit calculate. Once you hit calculate, you will have all the informations. Enthalpies have come, entropies, internal energy, and specific volumes. And you can also match it with the property table. Property table over here. You can see at 90 you have saturation pressure, specific volumes, and you have enthalpies associated with it, and uh, entropies associated with that. So same thing you can actually do it here. You can also plot if you want. So TV plot I can do. It can tell me where it actually uh, the where your it's not. So this is the dome you are expecting, and on this line you will have saturation condition, and it will be somewhere here. Okay, so all sorts of plotting and all you can do actually in the EES software, right? So yes, any question? Uh, any question so far? If no more questions, I may leave. Let me take the attendance, and I will conclude the session then. Thank you.
Thank you, sir.
ગયા સર.
મોજ કરો મોજ.
હવે લેક્ચર નથી ને?
પતી ગયા બધા.
રેકોર્ડિંગ હતું.
આજનું
ચાલુ
પતી 4 to 5 બી એક્સ્ટ્રા કશું છે નહીં.